Welcome to Excel 2010 Statistics video number 78. Hey, if you want to download this workbook, Business 210 Chapter 9 first, and there are two workbooks for this Chapter 9. This is the first one. Or you want to download the PDFs, and there's two PDFs. One is a huge 40 pages of handwritten notes, and the other one is a condensed version just of formulas, statistical formulas, and Excel functions. All right, so Chapter 9, we're going to do hypothesis testing. We're going to bring together everything we've done so far in this class. Now I'm going to start over in the PDFs. What is a hypothesis? A statement about a population parameter subject to verification. So for example, an official report claims the yearly salary for full-time realtors is $85,000. So if you are someone out there looking at this and you say, you know, that doesn't make sense for our region, you could go out and do a test to see if this statement is reasonable or not for your particular region. And that's the example. We'll use this example right here to examine the 5 steps of hypothesis testing. And then later videos, we'll look at lots of different examples. All right, so hypothesis testing is just a statistical procedure that uses sample evidence and probability theory to determine whether a statement about the value of population parameter should be rejected or should not be rejected. So here's our original statement. The yearly salary of full-time realtors is $85,000. So through our statistical procedure, we'll either reject this original statement or fail to reject this original statement. Now, if we reject, we will accept an alternative hypothesis. For example, if the claim is that the realtor mean is 85,000 and you believe in your region it's greater than, if the alternative hypothesis is greater than, we will reject this and accept the alternative hypothesis. However, we're going to be careful if our statistical procedure does not reject this or fails to reject this. We're not going to say that this is true because we're using statistics, right? And there is some room for error. All right, now, so our statistical procedure will allow us to do this. And this is basically what the book says. Very important. We'll always make some carefully worded, make a concluding statement about the population parameter based on our sample evidence. And we'll be careful in the way we word that. All right, let's go to the next page 2 in our PDFs. Here is a statement from an official report. The yearly salary earned by full-time realtors is $85,000. A researcher believes realtors make more than $85,000 in their region. Now, if we'll go out and take a random sample, and we get $85,595, right? We can't just say, oh, yeah, it is bigger. Look at this, it's 88,000. We can't say, oh, yeah, it is bigger, because this is a sample. So we must decide if the sampling error of the difference, that's $3,595, is that statistically significant or is it statistically insignificant? Now, I forgot the little double quotes there. Now, the cool thing is we already have all of the statistical and Excel techniques, formulas, functions, etc. from earlier chapters. Let's remind ourselves of what we did in Chapter 7. Chapter 7, we talked about the sampling distribution of X bar. And what was so great about that distribution is this is the distribution of all of our X bars. So we can go out and take a single sample. Ours is going to be 88,000. For our first example, we'll do 88,595, right? We can just compare it to this sampling distribution of X bar. And here's the deal. We'll learn how to pick a hurdle line. Anything beyond this hurdle, we'll say we'll reject the original claim and accept the alternative. Anything in this region less than the hurdle line, we will fail to reject. Now, this is just one type of test. This is a one-tail on the right test. We'll see how to do a one-tail on the left and a two-tail test. Now, in this example right here, see I have 85,000 here, and I'm directly comparing this $88,595 because it's out here it would then seem the original claim would seem unreasonable. Now, we could directly compare this, but that's not what we're going to do. We're going to calculate what's called a test statistic. And we've already done this. We've used the z distribution when sigma is known or when we're doing proportions, or the t distribution when sigma is not known. Now, the great thing about these test statistics is that they tell you how many standard deviations above or below the middle, or the mean in this case is. All right? So we'll use test statistics. And all it will do is, instead of having this value out here, we'll have some test statistics, which will tell us how many standard deviations above or below. Not only that, but that was Chapter 7. Last chapter, Chapter 8, we did confidence intervals. And remember, we ran a risk. Sometimes if we built our interval, it would contain the population parameter. Sometimes it would not. If we built a 95% confidence interval, we ran the risk that 5 of our intervals would not contain the population parameter. Now, in the textbook, they peripherally mention how to do hypothesis testing this way. And here's a picture, and you could do it. We're not going to do it this way. But the idea is the same, right? If we do 95% confidence interval, we run a 5% risk of making an error. Now, here's some other examples of statements about the value of population parameter. Is the new contribution solicitation letter more effective than the old letter? Contribution solicitation means we're sending out a letter to try and get contributions, right? Is it more effective than the old one, which got 15% contributions? Another possible question or original statement: is the manufacturer's claim that 16 ounces of ketchup is in each bottle? Is that reasonable or not? We'll actually do this one. Is the average wait time in line at McBurger's restaurant less than 3 minutes? Still another one: is the new machine faster than the old one? Right? So to answer all of these questions, we'll have an original statement. We'll have some alternative hypothesis, like maybe this new machine is faster, right? And we'll do statistical tests to decide whether we select the original statement or do we select the new one. Now, here's the test. We're not going to use the term original statements and new one. We're going to use some different terms. But here's the steps. There's 5 steps, and we're going to go through them in this video, do an example, and then talk about each step. And then in subsequent videos, we'll just go through the steps and look at a bunch of examples. First step is develop the null hypothesis. That is the original statement or the alternative hypothesis. Second, we select our level of significance, or alpha. We talked about this last chapter as being the risk that our population parameter was not in our interval. And we'll talk more about what that is in the context of hypothesis testing. Then step 3, we'll collect sample data, compute the value of the statistic, the test statistic, z or t, and the ever important drawing a picture. You know, when I was learning hypothesis testing, if I didn't draw a picture to visualize it, it was much more difficult. We'll see how to do that. And then there's 2 approaches which always lead to the same conclusion: the p-value approach to determine whether we're past the hurdle or not, and the critical value approach to determine if we're past the hurdle or not. Now, let's go over to Excel and look at an example. Now, I had at the top of each one of these sheets, I list, to remind you, all of the variables that we use. Mu is the population mean. Sigma is the population standard deviation. Most of the times we won't use that, but when we do, we can use the z distribution. Standard error, that's the standard deviation for the sampling distribution of x bar. I'm going to use the term SE, or the abbreviation SE. That's very important. That'll tell us how many standard deviations, right? And that's part of our calculation for the test statistics. The hypothesized value of the population mean, right? So the hypothesized value of the population mean for our realtor example is 85,000. That's the supposed mean for all realtors' annual salary. the catch-up example, it would be the bottle contains 16 ounces. So that will be our notation for that. Mu sub 0, that sub 0 means no difference from. Sample size is n. Sample mean is x bar. Sample standard deviation, when we're using t distribution, we'll use s. Alpha, that's going to be the risk of rejecting the original statement. And we'll see that original statement is going to be denoted by the term null hypothesis, or h sub 0 for no difference. Alpha is the risk of rejecting original statement when it's actually true. Test statistic, that's what we're going to use to determine whether to reject the original statement, h sub 0, the null hypothesis, or accept the alternative hypothesis, h sub a, for alternative hypothesis. Now, that's very important. This test statistics, and we've been doing this all the way back since chapter 3, either Z. We didn't learn t till just a few chapters ago. But the test statistic tells us what? Number of standard deviations above or below the hypothesized mean, right? So if you get a test statistics of 3 or 4, that is way out there. If you get a test statistic of 1, you know, that's not so far from the hypothesized mean. And then we're going to have Z or T. All right. And another thing about this, these videos I'm going to shoot for this chapter 9, you might want to put them on full screen in YouTube because I'm shooting it full screen. Here's our situation. Our first example. A statement from an official report reports that realtors make $85,000 a year. That's the national mean. Researcher thinks that realtors in the Des Moines area have a mean annual salary of more than $85,000 a year. At alpha equals 0.05, that's our risk of rejecting the original statement when it was actually true, is going to be 0.05. For our first couple examples, we're going to assume that we know sigma. Later, we'll see how to use the t distribution. Most of the time, you don't know sigma. Our sample size is 36. Our sample mean is that amount right there. Can we conclude that the realtors in the Des Moines area make more than $85,000? All right, when you're reading these problems or out there and you're in a situation, you want to think about a few things, because setting up the hypothesis test sometimes is the hardest part. First, we want to think of what is the point of view for this question here. Our point of view is we have a researcher who believes that Des Moines realtors have an annual mean greater than 84,000. Now, this point of view is going to be important because this greater than 85,000 will help us set up our null and alternative hypothesis. Now, what are we considering here? We're considering the population of Des Moines realtors. Even though we have this statement from a national average, we want to consider the population for Des Moines realtors. And what is our goal? Our goal is to run a hypothesis test to provide statistical evidence to support the claim that Des Moines realtors have an annual mean salary of more than $85,000. Now, again, this more than $85,000 is going to be important. If you're right, so that little comparative operator, and we could have said less than, or we could have said we think it's the same. That little comparative operator is the key oftentimes to setting up the null and alternative hypothesis. Now, the trick is if you have mu greater than 85,000, the fact that there's a arrow pointing this way will always tell you that it's a one-tailed test to the right. All right, now I want to jump back over to the PDFs just for a moment and look at page 7. All right. Step 1 is develop the null hypothesis, h sub 0, and the alternative hypothesis. The null hypothesis, h sub 0, that little 0 means no difference from. That's going to be the hypothesis tentatively assumed true in the hypothesis testing procedure. Based on sample evidence, we either reject h sub 0 or fail to reject h sub 0. Alternative hypothesis, h sub a A for alternative based on sample evidence. The hypothesis concluded to be true if the null hypothesis is rejected. All right, let's go back over to Excel, and we're going to see how to construct this. I'm going to blow this up real big just for, remember, the key is that mu's greater than, that arrow is pointing that way. All right, so I'm going to blow this way up. All right, the way you do this is you type H0, and then you type a colon. That colon, this is the hypothesis, null hypothesis. Colon says after this is going to be our hypothesis. Now I'm going to make this a sub. I'm going to highlight it in edit mode in the cell, and right-click, format cells, and then subscript. Now I'm going to click Escape. The keyboard shortcut is Alt-O-E. That is a ridiculous keyboard shortcut unless you're doing this all the time. And notice there's an underline. Now you could just check it and click OK, but there's an underline. So I'm going to Alt-B, and that highlights that, and then Enter. So the complete keyboard shortcut will be Alt-O-E-B, Enter. All right. Our null hypothesis, H sub 0, colon, and then you type a space, and you type mu. Now you could type the word mu, or you could do insert symbol, insert menu. Notice everything's grayed out because I'm in edit mode, except for symbol, because you can put symbols in. And then you have to hunt through and find the Greek letters mu. Now I usually have these, if I'm doing this all the time, mu, alpha, sigma, like that. Notice it's under recent. You click there and then click insert. I'm going to click cancel. The keyboard shortcut is Alt-I for insert, S for symbol, Alt-I-S. And then if you have them down here, you can get this by Alt-R. And then this is highlighted, so you can simply hit Enter, Escape. Again, that's ridiculous unless you do this all the time. Now, I'm going to Control-Enter and enter that. And I'm going to copy it down, and I'm going to cheat, and I'm going to change this to an A. Now, this is how every single hypothesis test we're going to do, one tail to the right, one tail to the left, two tail, is going to start off like this. And then you're going to have to decide the comparative operators. And then these two things will always be our hypothesized population mean. Now, I should have, I'm going to scroll out a little bit. The hypothesized mean is right there, so I'm going to put 85,000. I have that formatted as currency there. All right, so these two values out here are always going to be 85,000. So to make it easy on yourself, you can just always write this. There it is. It's right there. Then the only trick is how do you pick these? And it does depend on your point of view. And we'll see a bunch of examples, and I have it in my handwritten notes, and it's in the textbook too, how to help you decide. This one's easy. We already did it. The greater than symbol, our researcher was saying greater than, so I'm going to type mu is greater than. Now, if I just type a greater than, or sometimes we have to type an equal up here, it thinks it's a formula, so I'm going to type space and then greater than. All right, now what do you do up here? You just put the opposite. Now, you're going to have greater than, less than, and equal to. There's those three things. So I'm going to put space, less than, equal to. Now, remember, in Excel, we don't have that less than or equal to symbol. Actually, you do under insert symbols, but because we use this in formulas all the time, I'm going to do it that way. Now, here's the thing. Once you pick this, you just put the opposite here, and the equal sign always goes for the null hypothesis. All right, now I want to jump over to the PDFs. This is page 10. What I just said and showed you in the video is written here step by step. Again, you write H sub 0, H sub A. The colon means here is the hypothesis. So you write this. Then you decide on the comparative operator for the alternative. Sometimes you use the null hypothesis first because it's an equal situation. But a lot of times, putting the comparative operator for the alternative hypothesis first is the key. And then once you know this operator here, comparative operator, this one's just the opposite with an equal sign. All right, now, here it is. Here's our null and alternative hypothesis. Notice that symbol is pointing this way. That's how I know it's going to be an upper tail test. Now, we haven't figured out how to determine the hurdle yet, but this is what the picture will look like. Anything up here, we will reject the original null hypothesis and accept this one. Anywhere down here, we're going to reject that and accept this. Now notice it's everything this direction, right? Because we don't care. The original researcher says, I think it's more than, right? So all of this is not going to support that alternative hypothesis. Here's the 3 possible situations. This is the one we're doing here. You could do one on the low side or a two-tailed test. Now the next step is step 2. We have to pick alpha, and alpha determines the hurdle point. Level of significance, alpha. We saw last chapter, this was confidence interval minus 1 minus the confidence interval. Now, so that's going to determine our hurdle. Now we are, if we pick alpha equals 0.05, that means we have a 5% risk of rejecting h sub 0 even though it was true. Now I want to go down. I'll explain a little bit more on that in just a moment. Here's in the PDFs, you can look at this page 14. It shows you at different alphas how to set up the hypothesis and what the picture will look like. But now I want to talk about what that risk alpha really means. Now notice, this is the sampling distribution of x bar. The entire distribution is nothing but x bars. So my question to you, is it possible to get a sample, 88,595, out here? Well, yes, of course it is. We could actually get a sample. And this drawing over here on the next page, page 16, we could actually get a sample out here. And it's just because our sample numbers happen to have a lot of big numbers in it, right? Remember, sample says we take not all of the population items, but just some of them. So this distribution absolutely allows that there could be a sample this big, and the original statement is still true, right? So we just happen to get a bunch of big values. However, it's highly unlikely, right? It's very unlikely that we would get a value out here, especially when we calculate our test statistic. If it's 3 standard deviations, 4 standard deviations, you know, that is just very unlikely. So yes, it is possible, but we're going to have to pick a point. And so down here, we're just going to pick this point right here, and it'll be based on our alpha, our level of significance. That point, anything beyond this point, we will decide to reject the null hypothesis or the original statement. But that means what? This means that we take a risk of an error. So the official definition of level of significance, alpha, or type 1 error is going to be this: probability of rejecting h sub 0 even though it was true. Because remember, here's that 88,595. It's a sample. It's very unlikely that we would get a sample out here. So as a result, we're going to reject the original statement. But if we pick alpha 0.05, it means about 5 out of 100 times we will get this sample, reject the original statement, the null hypothesis, but it was actually true. So that's called a type 1 error. You can think of it as innocent but found guilty, right? Here's the sample. We got it out here. We rejected the original statement. But if it was true, it was innocent, but we said it was guilty. So that's an analogy. Let's scroll down to the next page, 18. Now, the designer of the test can control this risk. Here, alpha 10, alpha 5, alpha 1%, right? Or as we move this way, we reduce our chances of a type 1 error. So at alpha 10%, about 10 out of 100 times we'll have this error. Alpha equals 0.05, about 5 out of 100. Here, 0.01, about 1 out of 100 times. So if you want to avoid type 1 error, which means rejecting the original hypothesis even though it was true, you want to make alpha very small. And you can think of it, what about a drug company? If they're trying to prove that a new drug is more effective, they want to be sure, right? So they're going to make alpha small. And this is down here, and it's in the book. You can select alpha and control this risk. And you can think of it in terms of costs. The costs of making a mistake for a new drug is maybe it makes people sick or kills them. The cost of a manufacturer quality control making parts for an airplane, right? If the parts aren't correct, then the airplane crashes. So if the costs are high, then you make your alpha risk of type 1 error very small. All right, that's type 1. There's also a type 2 error. That is, h sub 0 was false, but we failed to reject h sub 0, which means we failed to reject the original hypothesis even though the alternative was true. All right, innocent but found guilty is a good analogy for type 1. Guilty but found innocent is a good analogy for type 2 error. Now, because we're controlling for alpha, we can say except h sub 0 in our conclusion. The flip side of that is type 2, also known as beta. Because we don't control for beta in this textbook here, we're never going to say except h sub 0. We're never going to say if we failed, we're going to say fail to reject h sub 0 instead of the original statement, null hypothesis is true. All right, let's go back over to Excel. All right, so alpha, we are for this example going to say 0.05, right? We don't necessarily need to say 0.01 here because we're just making this report, and maybe we're going to publish it somewhere. It's not like it's going to determine a drug or a part or something like that. Now, step 3. We are going to list our variables, make some calculations, calculate our standard error and our test statistic, and draw a picture. Now, let's see if I can right-click the comments here. If you see that little red thing here, right-click Show. The pictures, again, I don't know what I'd do without the pictures. So there's our picture. We've set this up. Alpha, 0.05, that's a risk of rejecting the original null hypothesis when it's true. That's going to be our hurdle. Alpha determines the hurdle. Beyond this point, we will say the sample error is statistically significant. Below it, we'll say it's not statistically significant. We have this line here, and you draw this picture. Everything above here, reject the original null hypothesis, accept the alternative. Everything down here, we're going to fail to reject. I can see when I made this drawing, I didn't finish this, but we have it right there. All right, now we have sigma, and that is 12549, I think. Later, we'll see how to do that. Use the t-distribution when we don't have the original sigma. We don't have this, so I'm going to put NA. The test statistic to use, what determines it for our test about a population mean is sigma. We know sigma, so we're going to use z. We are going to calculate our mean using the average function. I have the values right here. Control-Shift-Down arrow. Shift-Enter. So we have 88,595. Our alpha. The type of test, it's either going to be 1, 2, 3. I'm going to say one tail to the right. Again, the picture tells us that that little operator more than helped us there. Standard error. You can scoot this out of the way, no problem. Our formulas are there, but it's the same. We've been doing this for a while here. It's going to be the sigma divided by the square root of our n, which I didn't calculate yet, but I'm going to click there, close parentheses. It'll give me a divide by 0 error, but now I'm going to come up here. I have numbers over in that column, so I'm going to use the count function. Later, when we're doing proportions, we'll see how to use count when there's words. Right, so there's an n equal 36, so now our standard error. So this is the standard deviation for the sampling distribution of x bar for our test here. And finally, our test statistic. Remember, we take the particular x minus the mu divided by the standard deviation. Now, that's our notation for hypothesis testing, but we've been doing this since chapter 3, right? It tells us how many standard deviations above or below. So I'm going to say particular value minus our mean minus the hypothesized mean. I'm sorry, sample x bar mean minus hypothesized mean divided by our standard deviation, which is our standard error. 1.71 standard deviations above. All right, now, step 4. There are 2 ways. We have this hurdle. There's 2 ways. We can either use the critical value, which means we'll get some test statistic, and if it's past here, we'll call this the critical value. If it's past here, we're going to reject the null hypothesis, accept the alternative. There's also a second way. We can, once we have our test statistic, you can actually calculate the probability of getting that test statistic or more. So let's look at the picture. There's the picture right there, and then we'll do our calculations. Again, a picture tells 1,000 words. Right? So there's 2 methods, the critical value method and the p-value method. Critical value method, we'll see in just a moment how we already have done both of these calculations before, but now they have different names. Critical value, that's just at alpha, what is the z? 1.645. So that means if we get a test statistic, which you can see we did here, that's bigger than that, then we reject the null hypothesis and accept the alternative. That's one way, critical value. Here's the test statistic. It's going to be 1. We already calculated about 1.72. Well, if you take that z and calculate the probability, it tells you the probability of getting that or more. And the nice thing about that probability is you compare it directly to our alpha. Also, the p-value is nice because once you get a probability, you know the for this z, about 4 out of 100 times we'd have this error. So if you get a p-value that's very small, you know, 0.01 or 0.005 or something like that, then you know that's like 1 out of 100, or 0.005 would be 1 out of 200. Then it's very unlikely, and the p-value actually tells you the likelihood or the probability of getting that, which is useful. Now let's go ahead and calculate this. If we have a probability, we can calculate the z by using our norm. And I have right-click, unhide. I have the formulas over here. And actually, let me show you something amazing about these PDFs. Way at the end here, I have actually, let's look at this. On page 27, there's our test statistics. There, 28 has the test statistic for the proportions. And then this page right here, this is page 30. So this picture right here tells you for upper two-tail and lower tail tests what Excel functions to use for z and which ones to use for t. On page 31, this lists the actual picture, how you'd set up the hypothesis, the test statistics, the rejection rules, and the Excel functions. And then page 32 2 shows you for proportions, and page 33 shows you everything for the t distribution. Let's go back to Excel. All right, step 4, the p-value method. We have our test statistic, and we want to calculate the probability of getting that test statistic or greater, and then compare it to alpha. The rejection rule is very simple. P-value, anytime it's less than or equal to alpha, we reject h sub 0 and accept h sub 0. Otherwise, we fail to reject. Now look at this picture here. Right? We already, the idea of a hurdle is what we should have in our head, but obviously that probability is smaller than the probability for that whole hurdle or greater, so then we would reject. If we're on the other side, it'll be the same thing. Smaller probability than alpha, then we reject. Well, let's do the p-value first. All right, we have our z, so we're going to do equals norm.s for standardized dot dist. Dist, you give it a z. Remember, this is the s function, so you throw in a z, and it gives you the probability. Now, comma 1. The false or 0 is for charting. We want 1. And remember, how do these functions work? They always go from negative infinity up to the z you put in. So that's not going to work. That'll give us all the probability. We want the upper. All the probability is 1, so no problem. 1 minus that. There it is. So our probability is 0.042 using our rejection rule. Because this is smaller than our alpha, we reject the null hypothesis and accept our alternative. That's one method. The critical value method. Again, we need to actually find a z that marks where alpha is. And that means any test statistic z past that will reject. Now, when you're doing critical value, and we'll do, in coming up videos, we'll do a lower tail and a two tail. You have slightly different rejection rules. So our rejection rule here is if the test statistic is, it's not less than, it's greater than, right? Because we want, down here you can see anytime that this is bigger than that. So our rule is going to be test statistic greater than or equal to critical value. Then reject the original null hypothesis and accept h sub a alternative. Otherwise, fail to reject. All right? Let me move this over here. All right, so if we use the dist to get a probability, we use the inverse to get an actual z. So I'm going to do norm.s. And you see the dist? The dist, you throw in a z, and it gives you probability. The inverse, you throw in a probability, and it gives you a z. Now, probability, well, we want 0.05 probability. Well, wait a second. Remember, negative infinity to whatever we put in? That's not it. So we want all the probability up to that hurdle marker. So we have to say 1 minus. All right, so 1.645, that's our hurdle. So then our conclusions. Now these two methods will always lead to the same conclusion. The nice thing about p-value over critical value method is that it gives you a probability, right? So once we have done our sample data, set up our hypothesis, run our samples, calculate our test statistic. We had two different methods to determine the position of that test statistic. And now we write a conclusion, right? So one possible conclusion we could write, because p-value of 0.043 is less than alpha of 0.05, we reject null hypothesis and accept NA. We probably want to say more than that. Using the critical value, because the test statistic of 1.72 is greater than or equal to critical value of 1.645, we reject null, accept alternative. We still want to probably say more than that. something like this: the statistical evidence suggests that the mean salary for realtors in Des Moines is greater than the national mean, right? And we create our written statement based on the fact that we have statistical evidence. By saying the statistical evidence, it indirectly says, well, you know, there is some room for error here. Still another way, whoops, Control Z. I have these little formulas here in conditional formatting to pop these up. You know, I'd type this out here live, but I'm such a bad typer and speller that I'd mess it all up. All right, another way to conclude, at an alpha of 0.05, our sample mean of $88,595 provides statistically significant evidence that the mean salary, annual salary for realtors in Des Moines is greater than the national mean. Now remember, we have a potential for an error here too. So I'm going to say down here, we do run a 5% risk of a type 1 error, that we might say that the mean salary for realtors in Des Moines is greater than $85,000 when, in fact, it's not greater than $85,000. All right, hypothesis testing, that's a lot of fun. This first video was incredibly long, like 40 minutes. But there's so much to Chapter 9, even though the kind of basics of it, we had already been talking about it for a few chapters. We went through all the procedures. The next few videos, I'll just show you lots of examples of calculating and concluding. All right, see you next video.